Okay, can I go on? Good morning to the survivors. This is the last day of our symposium. It's for me a real pleasure to introduce you Damien's book from Argentina. There is the second part of the mini course which we began 2 days ago. It was on Thursday, right? About substructural approaches to logical concepts. So thank you very much, Damien, and to you the floor.
Thank you very much. I think I will listen. Yes. Is it charged? Yeah. So that I can not shout. Okay. Okay. Yeah, this one's good. Okay, cool. Thanks everyone for being here. I will talk in English because some people from Brazil perhaps would appreciate me not being so porteño in my Spanish. So again, disclaimer: if you have any questions, if you have any questions or anything that you want to ask, you can ask in Spanish, Portuguese, English, whatever you like. And you can feel free to interrupt me whenever you feel that you need to. Okay, so today is the second part of this mini course, this tutorial. You can find the material here on this website. It's rebrand.ly/substructural. There you can find the slides for past meeting, for this meeting, and a couple of notes that I put together with the content of the last meeting. I haven't put notes with the content of this meeting because the content of this meeting will comprise two separate papers that we're writing. So one of them I will mention covers a sort of a model theoretic results, and the other one proof theoretical results. One of them is finished, so if you want, you can ask me. The other one is in progress, so that one will have to wait. What else? The content of this meeting is more than anything original work. So, and it's work in progress, at least some of it. So, hopefully it will be of your interest. We think that it isn't out there or already published. So, hopefully it will interest you. So, let's get right into it. Okay? So, let's recap a little bit. So, we were discussing last meeting different conceptions or different approaches to substructurality, and we were discussing the fact that there's sort of a received view in the literature of logical consequence or substructural logics coming from the science of the logic and whatnot, saying that substructural logics are logics that when we think about them from a proof theoretic point of view, they are lacking or absent of a certain structural rule in the presentation. And when that happens, people usually focus on the external consequence relation. So there is a sort of aspect of the derivability relation of the calculus in question, and that renders a Tarskian consequence, right? So substructural logics are Tarskian logics, which have peculiar or funny or different looking conditionals more than anything. Also conjunctions, disjunctions, maybe even ligations or complex. Okay, so the received view treats substructural logics as non-classical logics, although Tarskian, right? But our view, or sort of the view that some philosophers have been working on with substructural logics, focus on substructurality as a phenomenon happening at the level of logical consequence itself. So, right, it means that taking away some of the structural rules sort of induces a notion of logical consequence, where some of the abstract properties like reflexivity, monotonicity, contraction, transitivity, or not is lacking from the definition of logical consequence itself, right? So the notion of validity is not Tarskian. So this was a big aspect, and we discussed how to distinguish things or how to know whether a system is substructural if you have your own, looking at it from a model theoretic point of view and from a proof theoretic point of view, especially coming from sequence calculus. And for that, we focus on meta-inferences. So structural rules are sort of meta-inferences, and that means inferences connecting sets of inferences. For the proof part, we have at least two criteria. One of them is admissibility, which is preservation of probability, and the other is drivability, which is preservation of probability under extensions, let's say. Okay, so and then we have also the model theoretic point of view, which relies on having a present notion of logical consequence, counterexamples, certain structures, models, or whatnot. And for that, you can take global validity, which is preservation of validity from premises to conclusion, or you can have local validity, which is preservation of satisfaction, or basically the absence of counterexamples. Okay, and that is sort of a more modern thing to it, looking at it at possible extensions. And we were discussing in the last part of the talk the possibility of having these things match, and we mentioned that admissibility and globability under certain well-behaved conditions, like for example, some incompleteness for the calculus in question, they coincide, okay? Because one of them is preservation of validity, one of them is preservation of probability. Hopefully, probability and validity coincide if you have some incomplete system. Therefore, they are the same, okay? And then local and validity and probability do not always coincide, but and in fact, this is a result sort of discussed by Humberstone and Garson and other people, and we also published something about that together with Fox in the group. But under certain, very reasonable conditions, basically having canonical sequence calculus, that is sequence calculus with introduction rules which behave normally, let's say, and also have side formulas or have context. Right, so they are very general in their presentation, and they do coincide. And even if you take away some of the structural rules, these notions still coincide. So if you focus on some structural versions of these systems, then local validity and durability still match. So it's very reasonable to think that local validity is sort of a model theoretic characterization of durability, although that's not absolutely entirely general. Okay. So this is our starting point for this presentation, and now we're going to go a little bit forward, and I'm going to tell you about some original work that we have been doing, building on these sort of very general, very broad results about, let's say, all systems, all semantics. Okay. So our aim today is to discuss. So I will try to introduce you to some substructural systems in these alternative results, so that I call the parastructurality. Okay, so these will be systems where the resident notion of logical consequence is going to be non-Tarskian, or at least they will have non-Tarskian extensions. And I'm going to present substructural logics which have a very interesting relation to classical logic. And this is a very peculiar fact, right? Because we usually think of classical logic as being a Tarskian structural system, and we usually think of that when looking at their inferences, right? And in that regard, the systems that we're going to present will be completely classical. But when we look at the meta-inferences, and in fact, when we look at the derivability relation of the company, and we look at the local validity of the intended models, they will be non-transitive, okay? So therefore substructural. So in a way, what I'm going to present has been called in the literature, at least in philosophy, by some colleagues, substructural presentations of classical logic, right? And it is not to mean that in the received view, you take a calculus, you take away some of the rules, and the external consequence relation is classical logic. It's something completely different. What we mean is that you take a calculus, you take some of the rules, the probability of the sequence is completely classical, but the derivability relation altogether is not classical in a way. And you will see that actually some very well-known results already speak to this. Okay? Actually, Jensen's Hausach's results of the eliminability of cut already speaks to this. But we are sort of broadening that, okay? So we will be focusing on systems presented model theoretically presented frustratingly, where we have the same valid inferences, or let's say the same derivable sequence that we usually have in classical logic, but the meta inferences will either have a different derivability relation, or we have a different set of local validities. Okay, so hopefully we'll be able to cover that. And again, if you have any questions, because some of the techniques or the notions will be very sui generis, please let us know. Okay. Good. So we're going to discuss more theoretically semantics that will render the same value inferences than classical logic, but since we're going to focus on substructural and in particular non-transitive systems, and of course you can think perhaps about other versions of classical logic, substructural based versions of classical logic, where perhaps contraction is invalid, but all the other structural properties are valid. Perhaps monotonicity is invalid, but all the other, etc., etc. Then, since we're going to focus in non-transitive versions, then cut is not going to be generally valid, or at least not in an unrestricted way. Some cases will have restricted versions of cut, but not the general version. Okay, so hopefully that's interesting. And when we look at it theoretically, what we mean by having a substructural representation of classical logic is that we're going to present calculus, where the set of the variable sequence is the same as classical logic, or LK, the system that I presented the other day, but not all structural rules are derivable, and in particular, cut is not derivable in an unrestricted or general form. Maybe some versions of cut will be derivable, but not all versions of cut. Okay, so we'll get there. Okay, so let's start with the semantics. Okay, so if we want sort of a substructural representation of classical logic, where that is not transitive, what we ought to look at is, or we can look at some semantic representation of classical logic that renders the same valid inferences, but when we look at the meta inferences, the only structural rule that is invalid in that, and by that we mean locally invalid, is cut. So we need to think about the definition of logical consequence that will keep everything almost the same as in two-valued Boolean logic, but only cut will be invalid, right? Only transitivity will be valid. And for that, we go to work with something that is called strict tolerant consequence. And in fact, even though this might seem a little bit weird or odd to you at the beginning, you will see that actually this definition of logical consequence is going to be completely standard and familiar to you. Just that it's a different, we're looking at it at a different light, under a different light. Okay? So this has been presented in some work by Cobrero, Segre, Ripley, and Van Roy in the recent years, right? But actually the algebraic work done with this notion of consequences done by Polish colleagues, mainly Frankowski and others, okay? So you can look at references later, but that's the point, okay? So consider now, just to understand strict tolerant consequence, consider the usual notion of classical consequence, right? So when we have classical logic, two-valued classical logic, we usually think about truth specification. We have two-valued Boolean logic, and we think about truth specification. But actually, if you think about it more, let's say conceptually, in a deeper understanding, what you have is that you have truth, you have falsity, and basically nothing can be true and false at the same time, and everything has to be either true or false. Okay? So when you are stating that valid inferences should necessarily present truth, you're actually stating four different equivalent things, right? Which happen to be equivalent if and only truth and falsity are mutually exclusive and jointly exhaustive, right? And these four things are the following. So, on the one hand, necessarily, if the premises are true, then the conclusion is true. That's the good old definition that we always sort of give to our students and in our talks and whatnot. But also, if truth and falsity behave in this way and relate to this way to each other, we also say that if the premises are not false, then the conclusion should be not false, okay? So that's another way of looking at the very same phenomenon, okay? So the first one, we'll call it strict consequence, because it says that if something is true, then something else should also be true. And the second one, we'll call tolerant consequence, because it says that if something is not false, then something else should be not false, okay? So it's a preservation of truth in one case, preservation of non-falsity in the other case. And then we have this different way of looking at things, which would not be sort of preservationist in this sense, where we have that if premises are true, then the conclusion should be not false, right? Which is the same if truth and non-falsity are the same. But nevertheless, it is an equivalent for stating facts, right? And then also to be exhaustive, we have that if premises are not false, then the conclusion should be true, okay? And everything coincides if truth and falsity relate in the usual, traditional, let's say, received way of looking at things, right? The classical. But if truth and falsity can diverge in some way, so for example, if we allow for things to be neither true nor false, that is, what do we think about contingent futures, vagueness, indeterminacy from a semantic point of view? Perhaps we're thinking about certain abstract structures, whatever we're thinking. If we allow for sort of a wedge to be, put between truth and falsity, then these definitions will really have a different effect, right? And this is where things start to get a little bit interesting for us. So we're going to focus on this strict tolerant notion of consequence, and you can already see that if we allow for something to be neither true nor false, okay, then the notion of logical consequence that's going to be rendered by this notion that is actually pretty near to our classical understanding is going to be non-transitive, okay? Because we're going to go from something that is true to something that is not false, then we're going to go from something that is not false to something that is false, and that's not going to be problematic, right? Because there's not going to be any, let's say, violation of any norm. But we will not be able to chain those two things, right? Going from something true to something not false, and then from something not false to something false, but we will not be able to build a bridge from something true to something false. That's the definition of an invalid argument, okay? So this very notion of strict tolerant consequence, if we allow, only if we allow for certain things to be neither true nor false, coming from whatever motivation you like, from your philosophical, computational, mathematical realms, then this is going to give you something which is, strictly speaking, non-transitive in this local way, okay? And more importantly, it's only going to be non-transitive. So it's not going to mess with reflexivity, with contraction, with exchange, with monotonicity, or with associativity. So everything else will be fine, but non-transitivity will sort of be brought into the picture of how to understand logical consequence. So let me just state a little bit more generally. So something, we say that a set of sentences gamma implies a set of sentences delta, and this notion of logical consequence is supposed to be multiple conclusion, the conclusion should be read disjunctively. If you don't like this, just take a single conclusion and it will be agreeing. And we should consider three value evaluations here for our work today, but actually this doesn't really affect, right? So strict tolerant consequence says that an argument is valid if and only if there is no valuation, no assignment, no way of considering all the premises to be true and all the conclusions or the conclusion to be false, right? So again, if we're in the two-valued situation, this is just truth specification, nothing funny. If we're in a three-valued setting, where things can be true, false, or perhaps neither, then this is going to give you something very different. So our question then will be, okay, so which kind of different alternatives of looking at the connectives, the usual negation, the junction, disjunction, even perhaps the repetition and whatnot, which way of understanding their behavior gives you classical logic when entertaining this notion of logical consequence, right? And that's our question here, and that's sort of one of the aims that we set for ourselves at the beginning of the talk. Okay, so this is sort of the goal, right, that we want to achieve. If we want to present a substructural version of classical logic, looking at it from a modern point of view, then the question, and by that I mean a substructural and in particular only non-transitive version of classical logic, then we should aim for a notion of logical consequence that in general only invalidates Kant, locally speaking, and all the other structural rules are fine. And we should also aim for certain sets of valuations, three-valued valuations that is, that when paired with this notion of consequence give you exactly the same valid inferences as classical logic, nothing else, nothing more. Okay. Question is, which are all those, right? Which are all those structures that when you pair them with this notion of consequence, give you exactly classical logic, okay? And more than anything, if you arrive at a question for those, how is there anything deep to say about these particular structures and why not some others, right? Okay, so let me just show you what is the answer, what are the answers to this question, and how can you go about having a deeper understanding of these results, okay? Of course, first of all, if we are thinking about three-valued evaluations, so we should be a little bit more precise about what kind of evaluations we are aiming at. And of course, you may say, well, evaluations are functions. So yeah, basically all functions. But since, you know, in semantics and in many semantics, we always have some new techniques and new things that we can use. We can look at generalizations of evaluations. And in particular, we can look at evaluations speak of at least two flavors. So the usual evaluations would be functions assigning each proposition a truth value in the codomain of the function. But we can also think about non-deterministic evaluations, and that is relations from the set of propositions to a certain set of truth values, such that when we have complex sentences, evaluations are sort of restricted to a set of truth values that can be the output of the intended operation. So we have some freedom, some non-determinism, but not everything can be legitimate or legal in that way. So what are we going to discuss today mainly pertains to deterministic evaluations. So we haven't yet to extend everything that we prove to non-deterministic evaluations. That is sort of the caveat for the results that I'm about to present, okay? So if you are interested in non-deterministic semantics, which are super cool, super interesting, allow you for a lot of things, and I can think just off the top of my head, a lot of interesting things about prior consistency, especially in the Brazilian tradition of Da Costa and the logics of Roman inconsistency and whatnot, and also modern logics, a lot of things. Be sure to check out the work of Anna Samansky and other. Okay, so they've done amazing things with that, these ideas, and there are a lot of applications. Okay, so be sure to check that. But I'm not going to work with non-deterministic semantics today, at least. Okay, so we're going to look at deterministic evaluations, three-value evaluations, that is, and we're going to ask our preferred question that we said before. And for that, we need to sort of canvas the landscape and make a few distinctions for everything to be tractable, right? And these divisions will be key to presenting our results. So when we think about tree-value evaluations, we will see ourselves as working with 1, 0, and 1/2, and that means truth, falsity, and neither true nor false, or just truth value gap, something like that, okay? And when we look at these 3 truth values, we can, if we like, order them in some shape or form. Of course, we can use the order of the rationals, that is completely fine, but we can also use this order, which is called the information order. And for that, you can check, I guess, many words. One of them that I refer here is Scriptis, all Scriptis, outline of a theory of truth, but also mainly Melfitting's works on bilattices and whatnot, where you have information orders and truth orders, and you can understand them in various ways. So when you have an order, the immediate thing to think about is monotonic operations. Okay, so ordered operations that preserve this order in some shape or form. Okay, so we see the universe of all possible tree-value evaluations as being divided into big families. Okay, so one of them is the monotonic schemata. So the monotonic schemata basically are truth values, or ways in which the operations work that preserve this order. And of course, for monotonic operation, you know how these work, and for the NER operation, you have just the generalizations of that, keeping track of the coordinates. Okay, and then we have the non-monotonic ones. So basically, either a scheme is monotonic or it's not monotonic. And so that's our first sort of just distinction in the realm of these truth evaluations, right? Okay, so and all these results that I'm about to give you are included in a paper that is under review, where with some colleagues, Bruno from Argentina and Paul and Emmanuel from Paris, and colleagues from the École Normale Supérieure, we sort of convey these results and try to explain them and prove them thoroughly. So the first result, and sorry, so one more definition before going into the results. Also, regarding the tree-value evaluations, since these evaluations can be widely different between themselves, we not only have the monotonic and the non-monotonic ones, but also, since truth and falsity are part of the toys that we're playing with, we might want to look at evaluations that behave with regard to truth and falsity, just like classical logic or two-value Boolean logic behaves, right? And those we call Boolean normal evaluations, okay? And this is a sort of a definition that can be found in the work by Nicolas Fleischer against the 60s. So basically, the idea is classical inputs, classical outputs. Otherwise, the functions can be monotonic, non-monotonic, or whatnot. Okay. Yeah, absolutely.
No, coming back to the non-monotonic or monotonicity.
Yes.
I mean, here more than the valuation being monotonic or non-monotonic, it seems that what plays the role of being monotonic or not is the operation, is the connective.
Yes, the connective. Yeah, and what we mean by evaluation being monotonic is that the way that the function assigns the truth value to complex formulas complies with monotonic operations.
Yeah,
exactly.
But you may have both, say, connectives that behave monotonically, and of course, connectives that behave non-monotonically.
Exactly. So
you may have both. Okay.
Absolutely. Thank you, Luis. Yeah. So we actually think about, when we think about classical logic in this way, we tend to think at least in this work, and there is nothing really, hinging on this. We think about the language of negation, conjunction, disjunction. We can talk about any language, but when we think about this language, we think about operations being monotonic or not, so negation, conjunction, disjunction being monotonic or not, and also being Boolean normal or not, and the whole valuation being monotonic or not if negation, conjunction, disjunction behaves in that way. So if some of them behaves monotonically, but the other not, then the whole thing is not. Because for it to be monotonic, everything has to be, right? If not, something great. So yes, thank you very much. And when we mention about the collection of all these options, so let's say how negation works, how conjunction works, how disjunction works, we think about this as a scheme. So let's say a collection of truth values or descriptions of how the valuations should work, right? So we're going to talk about three value schemes. So operations are monotonic or not, schemes, and that is collections of operations, are monotonic or not if the operations themselves all are monotonic, and if some is not, then it's not. Okay, so thank you. Okay, so and again, the same for Boolean normality, and the same for every sort of characteristic that we're going to measure. Yeah. Okay, so we have Boolean normality, we have or non-normality, and we also have monotonicity or non-monotonicity. Okay. So our first result pertains these sort of valuations, right? In these sort of valuations, you will find probably have been entertained by you at some point if you work with many value logics, and in particular with three value logics. Okay? And these are the Boolean normal monotonic schematic, right? So basically, they are extensions of two-value logic with a third truth value, and the whole thing. So every operation, negation, conjunction, disjunction, every operation has to behave monotonically for the whole thing to be monotonic. And if you have that, then you have a Boolean normal monotonic schema. So that is a collection of truth tables that is Boolean normal and monotonic. When we have different options here, it doesn't mean that we are thinking about non-deterministic valuations. It means that we wanted to give you a summary, a very brief presentation of all the options. And it means that every way in which you specify these truth tables to get a deterministic truth table, so a truth table where each slot has only one element, every way that you take, so every path is acceptable. Okay, so every choice in each of these slots, it will give you a Boolean normal monotonic schema. Okay, good. So, and basically, if you just a pointer, so if you know about three-value logics, the Boolean normal monotonic schemas are every schema between weak cleaning logic and strong cleaning logic. And what I mean by between is taking into account the information order, right? So you start the weak cleaning one is the one where you have 1/2 whenever 1/2 is the input. So, and the strong cleaning, well, it's a strong cleaning, right? And whatever choice you make that will make you one little step closer to strong cleaning is something between weak cleaning and strong cleaning, and then you can have like a lattice of options. And all those are the Boolean normal monotonic, and nothing else is Boolean normal monotonic. Okay. First result, and it's actually a generalization of something that has been already discussed in the literature a lot. If you have a scheme that is Boolean normal and monotonic, and you have the strict tolerant notion of logical consequence, then it's going to give you classical logic. Okay. Although transitivity will be locally bound. So we have our first intended result, right? Our first set of three-value evaluations that when paired with the strict tolerant notion of logical consequence, you have classical logic in a non-transitive presentation. Okay. How to understand this? That's a good question. Okay. So basically, one way to look at this, and this will connect with the next semantic result, is that when you think about something being neither true nor false, you can think about it being undecided in some way. right? So in a way, the most you can get from a Boolean normal monotonic schema, and that means the strongest Boolean normal monotonic schema that you can get, which is strongly in logic, is the one that if the thing that is being assigned 1/2 would end up being either true or false, the interpretation of the whole operation will be fine, either whether it ends up being true or whether it ends up being false, right? So it's the strongest understanding of the logical connectives agreeing with the thing being undecided, being definitely true at the end or definitely false. And the monotonic ones are the ones which are compatible with that decision. So are below that in a way. Okay. Good. So this is one way to look at this. Of course, it may have conceptual holes, and I'm completely open to that. And I will be eager to discuss that if you find something to say, because I'm always trying to learn more about how to figure out this. So let's look about one step closer to our final answer in the semantic aspect. So we have this is a sufficient condition, right? If something is Boolean normal and monotonic, then it's fine. But what else? Okay. So look at these other schemes. Okay, we have now sort of given information about the monotonic schemes. What about the non-monotonic schemes? What non-monotonic schemas are fine, right? So this hinges on quite a number of definitions that I'm not going to give you because they're really convoluted and there's no point of wasting your time with that. But of course, you can look at the paper if you're interested. So basically, the non-monotonic realm also divides itself into Boolean normal and not Boolean normal. And we're going to look into the Boolean normal non-monotonic realm, and we're going to distinguish there two families which are safe and sufficient to have classical logic. And for that, we're going to do something which is sort of one step farther from what we discussed regarding monotonic evaluations. So when we discuss monotonic evaluations, we mentioned what if in the end this undecided proposition that receives 1/2 ends up being true or false. Let's look at the maximum information that we can get for either of those decisions. Here we're going to do it differently. So the idea is, what if we were to treat this proposition that is being assigned 1/2 basically as if it were true, or on the other hand, as if it were false. So it is neither true nor false, but when I do this choice, I'm going to focus on the not false thing and just pair it with truth, therefore. And in another opportunity, I'm going to focus on the not true, so neither true part of the description of neither true nor false. And I'm going to pair it with falsity, therefore. So when you do that, you basically are thinking, what if when I consider my three-valued operations, I were to replace each 1/2 by either a true or a false, and then get something that will basically be the two-valued truth tables if 1/2 were to be substituted by either true or false. So this informal explanation that I gave is an informal representation of a notion that we call collapsibility. So basically collapsing the 1/2 either into truth or into false. Okay, and of course something is collapsible. So an operation is collapsible. It is either truth collapsible or falsity collapsible. And the schema, so a collection of operations, is truth collapsible if each of these operations are truth collapsible or falsity collapsible. So when we focus on those, we are actually into the realm of non-monotonicity, because negation, when it goes from 1/2 to something that is not 1/2, it's not monotonic. So if we're treating the negation of one half as being the negation of something that is more importantly not false or more importantly not true, then we are in a non-monotonic graph. And conjunction and disjunction should sort of comply with this intuition. Okay. And these are a summary of all Boolean normal truth collapsible and all Boolean normal falsity collapsible, right? So, and a summary, again, I mean that when we have more than one option, it is intended to convey the information that every choice that you make to have only one value in this slot is completely fine, and it's going to give you a Boolean normal truth collapsible equation. So our next result is that if you have a three-value schema, and if it is Boolean normal and collapsible, and by that we mean either truth collapsible or falsity collapsible, then if you pair it with the strict tolerant notion of consequence, you're going to get exactly classical logic. But it's going to be non-transitive. Okay, so cut is not going to be locally valid. Okay, so this is our second result, and it's a sufficiency result. So if you have three-value evaluation, if it's Boolean normal monotonic, then it gives you classical logic with the strict tolerant notion. If it's Boolean normal collapsible and it's truth collapsible or falsity collapsible, it gives you classical logic. So now, for the final act of the semantic part, the very interesting bit is that this is all that you need to know about three-value evaluations for classical logic. That is non-transitive presentation of classical logic. Because basically, if a schema is not Boolean normal monotonic or Boolean normal collapsible, then it won't give you classical logic. And that means if it's not Boolean normal, it's not going to give you classical logic. And if it's Boolean normal and it's not monotonic or not collapsible, then it's not going to give you classical logic. Okay? And this is proved sort of painfully by going through each of the families that is being left out by this definition or these cases, and proving that we have counterexamples to things that you ought to have in classical logic, but you don't if you are not within this collection. Okay? Good. So this is the end of the model theoretic part. Okay? What about the proof theoretic part? Right? So we canvassed the semantic landscape, and we found which three-value evaluations, deterministic evaluations that is, give you classical logic, but invalidate cut locally. Okay? So give you non-transitive versions of classical logic. What about the proof theoretic part? Okay? So let's look at the proof theoretic part. Okay. So when we look at the proof theoretic part, what we're aiming at is different sequence calculus, okay? And we want of this sequence calculus to be such that the derivable sequence are the same as the derivable sequence from classical logic being presented, for example, by Gensen's LK system, at least the propositional part of it, okay? So we want them to have the same derivable sequence. But remember that our understanding of a logic being, for example, non-transitive and therefore substructural entails that some of the structural rules have to be non-derivable. So we're not focusing on admissibility, we're focusing on not being not derivable. Okay? And that means that it is substructural. So we're aiming at sequence calculus that will give you exactly all the inferences of classical logic in terms of the derivable sequence. But where cut is not going to be derivable. Okay? Admissible, yes. Derivable, not. That's our understanding of substructurality. Okay? And in fact, if you think about it, one case of a system of this sort is pretty well known to everyone working on proof theory, and in particular in sequence calculus, because Gensen himself presented a case of that when he proved his famous Hausat. So his result that cut is actually eliminable from LK. So what does that result mean? It means that if you take cut from LK, then you have the same derivable sequence. Okay, but when you take cut from LK, cut is not derivable in LK. It is admissible, but it's not derivable. Okay, so if you are interested, like some people are, in systems where the structural rules are not derivable but admissible, then LK without cut actually presents a case of this sort, and it is well known since the 30s. Okay. Of course, you might be only interested in the probable sequence, and therefore you don't see anything peculiar in LK without cut. But we are interested in some structural systems, and therefore this provides an opportunity to reflect on a peculiar system. Okay, so so this is one example, but our question will be, okay, this is one instance. Which are all the options, right? So we canvass all the three valuable options, which are all of the systems that give you classical logic, but where cut is not derivable. That is our goal in the second part and last part of the tutorial. Good. So one starting point to sort of reflect on this whole set that we want to characterize, and hopefully will be able to characterize, is that LK with cut has actually, as presented by Jensen or in the standard presentation, LK, and I did this the meeting before, LK is presented with all interaction rules, all structural rules, including cut. So when you take cut away, what you have is all the structural rules but cut, and only introduction rules. So we can think about the system resulting from this subtraction as LK intro. It's basically LK, only the introduction rules, and by that we mean the top to bottom rules. So the rules where you have something without connectives on top and with connectives in the bottom part of the rule, okay? But cut is not present, okay? All the structural rules, reflexivity, monotonicity, contraction, exchange, everything is there, cut is not there. The eliminability result also shows that cut is admissible in this different system, right? And that means that adding cut will not affect the set of derivable sequence. So it's the same, but cut is not derivable. So our question is this. So what are all the sequence calculus that have the same set of probable sequence than LK? So basically the same valid inferences than classical logic, but different meta-inferences, and in particular, where cut is not a valid meta-inference, and more in particular, where cut is not derivable. Okay. And for that, since calculus is a set of rules, we probably should state which rules are going to be fine to have in our calculus, because otherwise it's going to be absolute madness. I mean, what rules? I mean, I don't know. I wouldn't even know how to talk about these rules in a general form. Okay, so we're going to talk about rules, about certain well-behaved rules, and this will ring a bell from the meeting before. That will basically do our work. Okay, so let's go to it. So we will talk about calculi that do this. So present substructural versions of classical logic, where rules have to be of certain kinds, and these kinds are two different kinds. Okay, and this is the part. This will connect with the work in progress part that I was mentioning. So if you're interested in this, we can talk later. We can exchange emails and whatnot, because this is something that we're actually right now writing, okay, with the colleague in Buenos Aires. So when we think about calculi having introduction rules, right? So calculi where you have something where no connected is mentioned in the premises of the rule, and a connected is mentioned here, we think about introduction rules. And a way to speak generally and abstractly of well-behaved introduction rules is this idea that I was mentioning by Abron and Lahal and people in Israel, and it's called canonical rules. Okay? And canonical rules, so introduction rules, can be of a left form or of a right form. And I'm not giving you the exact details on what are the parameters here, so the gamma, the phi, and the p's. But basically, it says that you can allow any context, right? Gamma, delta can be anything. So to allow for additive and multiplicative, so shared context and same context rules, you can have any number of premises. So sometimes you have rules with only one premise, sometimes you have multiple premises, right? And the active formulas, so the phi1, psi1, and etc., these have to be sort of built with the propositions being referred here, right? So it is analytic in that sense, right? So there's nothing that can be here that is not here. Okay. And gamma and delta should relate to gamma 1, gamma n, and delta 1, delta n in a precise way. So this is a canonical rule, which is a generalization of an introduction rule. The new bit refers to possibly, currently, having not only introduction rules, but also elimination rules. Okay, and what do we refer to with elimination rules? Elimination rules are basically rules that tell you that if you have a certain complex formula, then you can go to the more simple parts. So, in a way, it's essentially looking at introduction rules and flipping them. So, elimination rules are sort of bottom to top rule in the same sense in which introduction rules are top to bottom rules. But look, there are some subtleties in this, because introduction rules, in the way in which sequence calculus is presented, can have multiple premises, but sequence calculus rules always have only one conclusion. So when you flip these things, you are already in a complicated situation. And that means that if we want to talk about elimination rules in a generalized, very abstract and broad way, that's not going to be exactly easy, okay? And this is the work in progress part that I was telling you about. And I'm not going, yeah, please.
Yes, so you are saying that this one of the three production and elimination rule is just reading the rules top, down,
Yes.
down, top.
Yes.
In computer science, we say that these rules are inverted, but it's not the case for every rule in something.
Exactly.
So
Yes. Yes,
you
exactly.
don't have this concept of giving this inversion.
Yes.
Or this inverted.
Yes, exactly. Yes, absolutely. So sometimes these rules are not invertible. So yes, some introduction rules are not invertible, and that means that if you have the conclusion, you can derive the premises. That's what invertibility means. And in that case, you might need to actually have elimination rules, which are not the inverted forms of the introduction rules. And that already poses a problem, right? So how to choose these ones, how to define them. Is there anything interesting to say about what the corresponding elimination rule is for a given introduction rule? Is there anything interesting about what the semantics is when you think about the semantic counterpart of that? This remark by you is completely in tone with what we're trying to sort of characterize. So yeah, and given that we are work in progress, we can discuss that later and exchange opinion, because we're trying to pin down the exact general notion that we should have. Because just like introduction rules can be seen as, so canonical rules can be seen as a generalization of introduction rules, we're trying to aim at co-canonical rules, which are the generalization of elimination rules. And I'm not going to give you a general form because of what Lourdes said. It's not obvious how to do that. And perhaps there is no one single form of a generalized elimination rule. Perhaps you have to account for many different generalized ones. And something is a generalized elimination rule if it is one of these forms, for example. But we're trying to settle on that, okay? So this is necessary to answer the question, which are all the sequence calculus for classical logic where cut is not derivable? And for that, we also need to account for elimination rules. Okay, let me see. Yeah, okay, so how a little bit more, and I'm going to go through that. So imagine here, in this slide, there is coherent, final, full-fledged definition, illustration of what a generalized elimination rule is. We have some approximations and some preliminary results in our draft with Bruno from Buenos Aires. But it was too sort of complicated to lay out here. And I didn't want for it to distract you from the fact that basically we're aiming at generalized elimination rules. Right? So you probably get the idea or the intuition behind that. Of course, the subtleties are super important, but that's the idea. So the question will be, what are all the sequence calculus for classical logic where you have generalized introduction rules, generalized elimination rules, where cut is not derivable, that still will give you classical logic? That's the question. Okay? That's the thing that we're aiming at. So imagine you have a final definition for that. We have a draft, but it's all basically on sequence calculus for classical logic where cut is admissible and not derivable. So that's the thing where we are trying to pin down exactly the answer to this question. So just as an approximation to this final result that we don't have as of yet, in parallel to the semantic result that we have of necessary and sufficient conditions, we don't have that full collection in the theoretical case, but we have some very strong leads, let's say, right? That I will show you and explain to you in a bit. And hopefully also give you conceptual explanations of why they work, okay? So we mentioned, okay, Gensen's result says LK minus cut still gives you classical logic. Cut is not derivable. Basically, LK minus cut, we're going to call it LK intro. It only has the introduction rules. So that means that all introduction rules, no cut, that gives you classical logic. So what about the elimination rules? Can we build some calculus with only elimination rules, mostly elimination rules, that also gives you classical logic? Is there any sort of symmetry there, duality, anything like that? To the best of our understanding, that wasn't explored. Okay, so that's when we wanted to play with this. And these are the elimination rules of LK. So basically, these are the rules that we presented the other day, the introduction rules. That is just upside down. And this connects to the late question the other day and Lula's question this day. Remember that we presented the multiplicative additive sort of presentation of LK. So the two premise rules were additive, the single premise rules were multiplicative. Why is that? Because these forms are invertible. And therefore, when we talk about the elimination counterpart, it's just flipping them. Okay? So that's why. So here we have these forms just flipped. And parenthesis means that we can have either of those. Okay. Good. So we have negation. Basically, if you have it in the left, you can have the negative of right and the other way around. And for conjunctions, if you have both conjuncts, you have both them by separated by a comma, etc. Okay. And we also will discuss some instances of cut, but not the full form of cut. So cut doesn't appeal to any particular thing when you mention that you're cutting phi, right? It's just any phi whatsoever. But you can say something specific about that fee. For example, you can say, this fee that I'm cutting, it's a negation, or it's a conjunction, or it's a disjunction, or it's a conditional, or it's something else, right? And if you specify these, you're looking at specific instances of cut. And you might end up in a situation where you have cut for negations, cut for conjunctions, cut for disjunctions, but you don't have the unrestricted form of cut because you have cut for propositions. Propositional atoms, that is, okay? So these are restricted forms. And even if you end up having all of them, you might end up in a situation where cut is not generally derivable elements. So that's also interesting for us, okay? So let's look at a list of appropriate systems that we already know of that are substructural, and by that we mean non-transitive, okay? So non-transitive presentations of classical logic, relatively speaking. First off, Genson's result, LK intro, so LK minus K, the system that he proved his house us about, okay? Second one, all the introduction rules and basically everything else that you want to add that is already admissible in the system. So if you have a system that gives you what you need, and you have admissible rules, you are not going to screw with your target. You're going to aim to nail it anyway. Okay? So in particular, if you start from the introduction rules and add all the elimination rules, it will still be fine. And we only pinpoint this option because we're going to talk, well, because our general question was about, what about all the calculi where you have generalized introduction rules, generalized elimination rules? And therefore, in particular in relation to LK, we want to see what happens with combinations of the introductions and the eliminations, okay? So introductions only, right? Introductions and eliminations, perfect. Only eliminations, what about that? I mean, if only introductions is fine, what on earth would make only eliminations not fine? Well, that's a very good question. And the fact is that only eliminations are not fine, right? So in particular, they don't give you that. And you cannot supplement it with, let's say, more elimination rules that will do it. So for example, you cannot add instances of cut and make it work. The proof for that, at least in our case, really depends on the bridge between the semantics and the productivity. So I'm not going to present it so as not to just confuse you, but if you want, we can discuss that. It's very interesting proof, and it bears on the fact that local validity and durability coincide. So we prove, given that the set of derivable sequence for elimination is not classical logic. So a good question would be, if extending all the intro rules is fine, and we know that starting from the elimination rules is not fine, what extensions of the elimination rules are fine? If we know that having all the introduction rules and all the elimination is okay, well, is there something in between all the introductions and some introductions, or no introductions? Okay, and we're going to discuss that, and also some options in the middle. Okay, and with that, I'm going to finish. Okay, so let's look at the introduction rules again, and let's separate them into two sets. The ones appearing in red, ones appearing in blue. The ones appearing in red are going to be called red intro. The ones appearing in blue, of course, blue intro. And if you look at these rules, you see that interpreting them semantically, let's say, the red ones tell you what happens if phi is true, and the blue ones tell you what happens if phi is false. Okay, more or less, let's say. Or if you want, in a more generalized way, what happens? The red ones tell you what happens if phi is not false, and the blue ones tell you what happened if phi is not true. Okay. Good. So what we know is that if you start from all the elimination rules and add only one half of all the interaction rules, but you cover this half conceptually thinking about what they say about how the formulas behave, then you actually end up with a satisfactory system. That is not the system having all the intro and all the eliminations. So having only half of the eliminations, appropriate half that is, you end up with a good result. So blue intro plus all the eliminations, perfectly fine. Red intro plus all the eliminations, completely fine too. Also, all the intro plus all the eliminations, we knew it was fine. So here we're sort of toning down a little bit, or just dimming down a little bit the interactions to a point where it's still fine. Okay. And of course, all these options can still be extended with admissible forms of cut that will still not give you the full derivability of cut. So it's still a non-transitive system. I mean, any of these is. But even if you want cut for negation, cut for conjunction, cut for disjunctions, it still will be non-transitive, and it still will give you exactly what we are aiming at. So now for probably the final bits, also look at the elimination rules. And let's also separate the elimination rules in two separate collections. One of them we call blue eliminations and red eliminations. And again, you can see that if you're reading them top to bottom, right, or bottom to top, you can always think about rules saying that if you have a counterexample to what's below, you need to have a counterexample to what's on top, and therefore it says these rules say that if phi is false, so the red ones think about the falsity of phi, and the blue ones think about the truth of phi, right? Because counterexamples mean that of the left and right formula. Good. So this is sort of the explanation of why are we selecting them in this specific manner and not in another way. Okay. And the interesting result is that we know that only the introduction. So we know that if we have all the intro rules, that's against the result, we're fine. If we have all the elimination rules, that's not fine. What about if we only have half of the introduction rules? No, that's not okay. So we prove that LK plus only blue intro is not enough, and LK plus red intro is also not enough. LK plus all the intros, so it's blue and red, that's fine, but that's already known, right? But half of them, no, that's not enough. Also, if we mix some of the intro and some of the links, so if we mix blue with red, so basically some rules treating, so stating what the behavior should be if we want to be focused on the falsity of the formulas, and then on the other hand, we'll be focused on the truth of the formulas. In one case for the introductions, and in the other case for the eliminations. This information is too incomplete for the calculus to be satisfactory, right? So mixing blue and red elimination and introductions doesn't give you classical logic. It's just not enough, okay? But interestingly enough, mixing the appropriate introductions and the appropriate eliminations, the blues and the reds, it does give you classical logic. So if you have enough information about the formulas being discussed, and enough information about the formulas being discussed means what happens when these are true or not false, treating them as introducing them, also eliminating from them, then that's enough for classical logic, and also the other way around. Okay, and interestingly enough, so you can think about this again as a lattice, right? So when you have like all the intros and eliminations, and also only the eliminations and only half of the eliminations, and then carving the way up. Okay, So that's exactly what you need to have. Again, you can supplement these with counts for negation, for conjunction, for disjunction. Still, you will end up with a non-transitive, meaning cat is not available. We have 5 minutes more, right? So
4 minutes.
4 minutes. Good. Okay. No, that's more than I need. I can do it.
Don't worry.
I can do it 3
We
minutes.
have to break it.
Okay. Okay. So please observe that as opposed to what I told you regarding the semantic results. In the semantic case, I presented a very complete picture, right? I told you exactly what are all the evaluations, deterministic evaluations that is pre-value, that when paired with a strict tolerant notion of logical consequence will give you classical logic, it still will be not locally valid. Here, I didn't do exactly that, right? So I only presented some cases. So in a way, an ordering these cases where you have minimal options, and then you can extend them with admissible rules so as to finally arrive to some of the cases which we already knew that were well behaved, okay? But we still lack a complete and general characterization of all the calculus that have, canonical rules and co-canonical rules, and that is something sort of that we hope to do in our future. And finally, some sort of shout out to something that we're going to present in the future. I promise that if you think a little bit about these results, you will see that there is a very strong connection between everything that we self-proof to do right now and every semantic result that was presented before. And in particular, that the notion of local validity associated to each of these calculi can be associated either with a monotonic Boolean normal variation scheme or with a non-monotonic scheme of the kind that we were talking about. So Boolean normal and either truth collapsible or positive collapsible. And you will see that the blue ones just sort of go with one sort of semantics and the red ones with another. Okay, so there is a bridge to be built there, and we are writing about that. But I thought it was too much to also make that mention here. That being said, I think that after this I only have my references. So let me, before finishing, just thank Samaria and Rafa a lot, and all of you a lot for being here and for your questions and discussion that we have in the hallways and whatnot. And hopefully that will interest you to keep talking and discussing these issues. And thank you very much.
Thank you very much, Damien. For me personally, very, very interesting. Some questions, please. Yes. You did the microphone.
Okay. Thank you.
So, thank you. It was very nice. I would like to ask you one question. Maybe I start with. So, there's a word, TPS. Okay. So they have this system for the group. I mean, there's no main connector. You can apply the rules, implicit rules inside as much as you want. And they have, for all the systems that they have two types of systems. One, the arrow up, and the arrow down. The ones with the arrow up are the what we control, and the ones with the arrow down are the definition. So there is already a system for best for measure. There's also something that they don't have using that. So there is a design. So maybe it's a good idea for you to take a look at this for putting reference.
Yes.
Then someone from there to verify your work and
yes.
You can send.
Excellent. Thank you.
Second thing, so one thing that's bothering me is well, in this work, they show that this fragments, they are consistent. So I didn't understand, and actually, when you talk about introduction, you do that since the rules are all vertical, of course, the other ones are also right. Okay. Why doesn't it work together?
Yes.
Because they show that it does work. You're telling me that it does not work. So
No.
missing something.
No, thank you very much. I guess that the answer is that cut does the work for invertibility. So if you have the intro rules, then the elimination rules are derivable, and that means admissibility is fine because all of the rules, if you have a system for LK, whatever system you want, all the rules of LK are going to be admissible, right? But the ability is the important thing. So, I mean, the rules, if by invertibility you mean the admissibility of the inverted rule, all the rules are going to be invertible in that way. But if you mean derivability, that's a different thing, right? That means adding the introduction rule and seeing if you can derive adding the premise and seeing if you can derive the conclusion. So extending. And for that, in LK, so that's basically the derivability of the elimination rule, of the inverted rule. And for that, in LK, cut plays a role. So if you don't have cut, the inverted rules are not derivable. That's why there's a difference between, say, LK intro and the full intro like that, right? So that's why there is a difference between LK intro plus elim and LK elim, right? Because in LK intro, the elimination rules are not derivable. And basically that's why. Does this answer something? Yeah. Yes.
Just also because, you know, the introduction, we have only introduction rules that you can,
yes. Yes. Yes, because you know, the fact is that, and you can see that if you have identity or reflexivity in the Sigma calculus and cut, if you start with introductions, you can derive eliminations. Derive, that is, not make admissible, derive. And if you start with eliminations and you have reflexivity and cut, you can derive introductions.
Yeah.
If you don't have cut, you cannot. So these are going to be different systems regarding derivability and therefore regarding derivable rules. So, and that's the very interesting part. And must confess, I was, and in a way, I'm still puzzled by these because there seems to be no symmetry. But this is what the results show.
Thank you. Other question, please. Hello?
Connection with the right one.
You did the microphone.
No, it's not necessary. Okay. It's clear that we talk about classical logic in different way. So, obviously, some people believe classical logic is to have only two values, and or transitivity is essential to classical logic. So, in this way, this system is not classical logic.
Yes.
Another conceptual point is this system is, in your sense, superstructural.
Yeah.
So classical logic in this way is superstructural logic.
Yeah.
So these are for me at least the more important point connecting with this conceptual discussion.
Yeah.
As you know, if you use strongly and use as the definition of logical consequence, the external logic or the logic of the meta inferences LP is not consistent. And do you have a similar result to the other family of non-strong cleaning scheme?
Yeah. So that's a good question. So let me just go to the semantic part. So I mean, for the case, yeah. So this sort of works. So this pertains to the connection between the proof theoretic and the semantic part. There are going to be some algorithm that are actually extensions of all the interaction rules plus some elimination rules. Those are going to be the ones that, if you look at them semantically, they correspond to the Boolean normal contracts. Right? And when you look at those algorithms, and if you think about the external notion of logical consequence that they induce, it's going to be Pascal logic, right? We talked about this enough. And in the case of all the introductions and all the eliminations, the external notion of logical consequence is going to coincide with LP, Graham Priest LP, the logic of paradox, the strong cleaning relations with tolerant notion of consequence, so there is non-positive perturbation, etc. The weakest one is going to be the one we have fast everywhere, right? That's going to correspond to the weak clean logic with a tolerant notion of consequence. But then in the middle, you're going to have some logics that are not as discussed usually. So you will have all the logics between weak cleaning and strong cleaning, but you will also have some logics that are even below weak cleaning. So because they will have non-deterministic semantics, right? So that's a bit that I didn't talk about, but yes. So the notion, and then for the Boolean normal, the Boolean normal collapsing have the same. So you have a lot of non-classical logics, parallel systems and parallel complete there. We haven't explored exactly which ones they are, but we have a proof that they correspond to the notion of externality. Yes.
Thank you very much. I think there is another question.
Yes. Thank you, Damien. That was very nice. As you know, some people think that it is the introduction rules what gives connectives their meanings, right? And some other persons are skeptical. They say, no, at least for some connectives, it is the elimination rule of this technique, for example, the condition they would say. So I was wondering if you have thought about the implications of this kind of a source of that sort of
Yes. No, thank you, Luis. I mean, this is a very good question because, well, in a way, again, if you look into the bridge between these proof theoretic results and the semantic results, again, I haven't talked about this bridge much here. If you look into that, when you have a definition of logical consequence, in this case, strict tolerant, then some of the rules are going to describe one half of the truth condition. Other rules are going to describe some half of the falsity condition. And by one half, I mean, let's say the relevant half. What happens if the components are true or false, etc.? What happens with the complex thing? And the other ones are going to describe what happens if this thing has this value, then the components should have that value, right? And perhaps some people could say that the rules that go from if the components are so and so, the complex thing is so and so, perhaps they might say those are the distinctive rules, right? But I'm not completely sure. And to be honest, I remember, at least when thinking about sequence calculus, I remember thinking like, why people presented with all the interaction rules? Why not all the elimination rules? Would that be enough? And then we realized that it is not. So perhaps there isn't, perhaps there is something special about the interaction rules. Or perhaps it is only a fact of how the sequence calculus is built, right? Something like, in connection with what Lourdes was pointing out, since sequence calculus is very asymmetric, lots of parentheses, only one conclusion. Maybe the fact that the elimination rules are not enough is a fact of how sequence calculus is constructed. But if it were in a different way, maybe the elimination rules would be enough. I admit that I think it is a very good question. I have no answer, but I would love to keep thinking about this.
Thank you very much. I think that our time is over, but if you want to make a little last question, we have lunch now. There is another presentation, so very well.
And if not, you can ask me anytime. You can shoot me an email, whatever you feel. It's going to be fine.
Could you say something
I will
about data elimination?
About calculation in what sense?
Well, usually, again, classical logic, data elimination for solve. What could it here where that is default?
Yes, so cat cannot be present in full form because otherwise that would be very good. But it is certainly the case that every form of cat that is going to be present, so cat validations, extension, conjunction, whatever, it's going to be eliminated because it's not going to be necessary to derive the target sequence. So you have some sort of cat elimination there. I mean, it is a restricted form of cat elimination, but it is. It's a form of elimination of a restricted form of cat. I mean, so that's the sort of parallel between the old results and the sort of results in these systems or within the systems. Yes.
Thank you very much.
Thank you.